and welcome to another lecture of Introduction to Astrophysical Fluids. In previous discussion, we showed that how using a very simplistic approach, okay, we can derive or we can obtain the criterion for convective instability of a compressible fluid. Okay. Now, in this lecture, we will derive the conditions or obtain the criterion for the instability against convection, okay, for an incompressible fluid. And this is known as the famous problem of Rayleigh-Bennett convection. Now, Rayleigh-Bennett convection is important for both the domestic life, where we can see the water is boiling, and I mean when the water is heated by some burner type of thing or a stove, you can see the water is boiling and convective type of motion takes place. And also this type of convection and actually proper signature of this type of convection can be seen in the solar surface, which we call the granules. Okay, now how this type of things can be obtained, I mean a bit more analytically, okay, how this type of I mean the condition for stability rigor, I mean depending on the various parameters of the system, how we can quantify such criterion, that we will learn in this lecture. Okay, so Rayleigh-Bennett convection, or which we often called as RBC, is important both for our household life and also for astrophysical contexts. So a gas, okay, which is in general compressible, we already have derived very simply the condition for stability, okay, against convection without formally linearizing the system of the equations in the previous discussion. And we said that in general we can do same type of analysis by proper calculations, but I mean that is a bit cumbersome, and actually in order to derive the Schwarzschild criterion of stability, we basically don't need to go through all this mathematical rigor, but this a very simple simple analysis would lead us to the same conclusion. Okay, so and we saw that if the system has a very if a system is in hydrostatic equilibrium and the system has a very important temperature gradient, okay, then the system has a much more tendency to get convective get unstable against convective motion. Okay, so now the thing is that that was very good for a compressible, fairly compressible fluid. So we can just perturb the density and take the mass of the or the blob of the fluid to another position, okay, very rapidly, thereby undergoing an adiabatic change. But now the question is, what happens if the fluid is a nearly incompressible fluid? Okay, can we do something like that? Well, the answer is not evident, and then actually one has to go through the formal analysis following the linearization process. Okay, then we have to go through linearization. Why? Because the simple thing is that if you really remember that when the fluid blob was, I mean a small mass of the fluid was displaced from one place to the other, then we said that the blob acts like a adiabatic fluid. Now adiabatic means P is equal to K rho to the power gamma, and gamma cannot be any other thing than the Cp by Cv, which has a specific value. Now if our fluid is incompressible, then the mass of the blob, I mean the blob of the fluid which is displaced should also be incompressible, right? So this type of adiabatic closure can never be applicable to that blob. And we all know that for an incompressible fluid, gamma actually should be equal to infinity. right? So this type of treatment which we did in the previous discussion cannot be applicable any longer here. Okay. Now the stability analysis of a nearly incompressible fluid, okay, was formally done for the first time by Rayleigh in the year 1916, and he did the theoretical analysis. But 16 years before that, Bennett actually found the experimental evidences of what Rayleigh recovered or really found by analysis. So Bennett was the person who experimentally developed the field, and Rayleigh was the person who theoretically developed the field. So combining both, we now talk in terms of Rayleigh-Bennett convection. Okay. Now, for the current Rayleigh-Bennett problem, first we have to consider a fluid is at rest. Okay, and the fluid should be heated from below. Just think of a kettle which is heated continuously by a burner or a stove from below. Okay, now if you just continuously heating the system, actually it is expected that, and you don't change the regulator of the burner, then after some time, actually you can assume that the heating rate is constant, or this is a steady heating rate. Okay, so that is our point of departure. We will come to that in a moment. Okay, now we can actually show the whole system in a schematic way in the figure below. So here you can see that we have a fluid at rest, and actually we consider an incompressible or nearly incompressible fluid. Okay, so we sometimes will call this as a liquid. Okay, so we have a liquid at rest in a container, and this liquid is heated from below. Okay, and due to the heating, there is the liquid is at rest, so there is a temperature gradient, you all know that. Okay, and the container's height, okay, the container's height is d, so the fluid is if we assume that the fluid is filling up the whole container, or the liquid is filling up the whole container, then the liquid is also filled up till the height z is equal to d. What is z? Z is nothing but the vertical upward direction. Okay, so this point where this is heated is z is equal to 0, and this is z is equal to d. Okay, so the burner temperature, which is now steady, okay, is called the TB, and the upper surface of the liquid, which is now kept at room temperature, we just call it as T small t, that is the T of top, and this is the T of bottom. Okay, so of course you can easily understand, in case of heating, TB is much larger than TT. Okay, now incompressible fluid simply means that it has a negligible variation of density with pressure. Okay, so that is something to be understood clearly. Okay, incompressible fluid does not blindly say that its density is an absolute constant. It is saying that its density is constant only against a change in pressure. But if we heat the system, if we change the temperature of the system, then the variation of density is non-negligible, or this is non-zero. Okay, and that's exactly what we will be considering here. That is, the density is a function of temperature only. Okay, now so as you can see from this setup, that liquid at bottom gets heated and become lighter, right? And when it becomes lighter, then it wants to come over the colder liquid above. Okay, because the colder liquid is heavier and having greater density, so this colder liquid wants to come down. So there is an up and down motion, and this is called the very popular convection motion, convective motion. You all know that convection motion is the macroscopic way of transport of heat, right, in a medium. Now, what I just said, that for an incompressible fluid, the density can only change when the temperature is changed. That can quantitatively be understood from a very basic kinetic theory knowledge, which we already discussed in some of the previous lectures, where we recall that P, or the pressure, is equal to the number density times the Boltzmann constant times the temperature. And this density N is equal to a function of P and T. So N is a function of P and T. If you write now N is equal to 1 by Kb P by T, then N is a function of P and T. For incompressible case, N is only a function of T. Okay, and N is totally is uncoupled from the variations of P. Okay, whenever there is a variation in P, N doesn't care. Okay, that is the meaning of incompressibility, that N is a function of T only. So density changes as temperature changes. Okay, how should it change? We all know if you heat the system for most of the usual materials, the density should reduce. Okay, because of the intermolecular distances increases, so the density should reduce when the temperature increases. Okay, and vice versa. So for a change dt in the temperature, okay, the internal energy also changes by d epsilon or dE. Sometimes, in some cases we can write epsilon, in some cases we write small e, whatever, but that is d epsilon is equal to Cp times dt. Cp is nothing but the specific heat of the material. Okay. Now if we recall the evolution equation for internal energy, you see always we make reference to those basic equations, fluid equations, which we derived. Okay, and that is the evolution equation for internal energy. Okay, and this is nothing but rho del epsilon del T plus V dot nabla epsilon is equal to divergence of K gradient of T. So this is the conductive term minus P times divergence of V. Now for our compressible case, this one is neglected. Okay, this one is neglected because of the continuity equation. Okay, and so continuity equation actually says another thing, that not only that rho is, not only is rho is indifferent of the variations of density, variation of pressure, rho is also, if temperature is constant, rho is also constant in time and space. That is also very, very important. And if you go another level higher, you actually can see that for an incompressible fluid, the material derivative or the Lagrangian derivative of the density also vanishes. So that means the density of a fluid particle is a constant in time. Okay, of course, when the system is not heated. Okay, now using d epsilon is equal to Cp dt, we actually can replace this expression over here, and you can easily find another equation in terms of T, or the temperature in absolute scale, of course. Del capital T del T plus V dot nabla T is equal to kappa nabla square T. This kappa is nothing but the thermal conductivity by rho times Cp. This is called thermometric conductivity. Okay. Some people also call it thermal diffusivity. Okay. Why thermal diffusivity? Because if you just think of the this system is static, then V is 0, then T is simply obeying an equation of diffusion type, del capital T del T is equal to K nabla square T. So K is another, it's a type of diffusivity. Okay. Now we are now ready to define an initial state around which we will make a perturbation. Okay, and when initially the system is in steady heating, So as I said that most of the cases we will start from a steady condition. Okay, so steady heating means the del T0 del T, T0 is that initial temperature, del T0 del T is equal to 0 and V is equal to 0. It simply says that this one is 0, this one is 0, so nabla square T0 is equal to 0. That means that when the system is in steady heating, there is a spatial gradient or of temperature. That means the temperature is a function of space, and this is called a stratification, okay, in terms of temperature of the stratification of the liquid in terms of the temperature. That means you can actually see static layers of fluid liquids of different temperatures. Okay, and if this is 0, then you can actually see that as we have just assumed that our system's heating is only in the vertical direction, so the temperature gradient can be effectively taking place in the z direction. Okay, so you can actually see that d2 T0 dz2 is equal to 0. So that is the initial condition. Okay, and it simply says that T0 or rather dt0 dz is equal to some constant, and that constant should in general be negative, because we know that the when z increases, T0 must decrease because the heating source is at z is equal to 0. So it should be some negative quantity, which is minus beta, where we assume beta is actually an algebraically positive quantity. Okay, so T0 will then be equal to minus Bz plus capital gamma. Okay, this is the constant of integration. Now at z is equal to 0, we know T0 is nothing but Tb, that is the burner temperature or the bottom temperature, and so gamma is nothing but equal to Tb, because at z0 T0 is Tb, so gamma is equal to Tb. Okay, now at z is equal to D, T0 is equal to T top, right? Temperature at the top, T small t. That's why then you can evaluate beta, which will be simply equal to Tb minus T small t by D. Please check all these steps. These are very much easy and can be doable. Okay. At an arbitrary small height z from the bottom, then you can in general see actually all we are thinking that all the even the like the height of the container D is actually not very much big or large. Okay, so we can simply say that the Z, which is a displacement, some arbitrary displacement from Z is equal to 0, has a moderately small value. Okay, moderately small value. I mean, although it can be an arbitrary height, but if it is within Z, D, and D itself is not very large, so this is a small height. Okay, that's why I add the point small later. So it's an arbitrary height Z from the heating ground, but reasonably in our study we are actually considering all the moderately small lengths or small heights. Okay, so for that arbitrary height, the initial density, matter density or the liquid density, will be rho 0, which will be equal to rho bottom times 1 minus alpha delta Tz, where delta Tz is the temperature difference between the heated layer, between the burner, the bottom layer and the height Z, and alpha is nothing but the volume expansion coefficient. Okay, so for volume expansion it will have, so if it is for the volume, then this could have been V0 times is equal to some reference volume 1 plus alpha delta T, but here for density it should be 1 minus alpha delta T Z, right? Now what is delta Tz? Beta is the temperature gradient, and beta times the Z And that's what beta times the Z with a minus sign gives us the temperature difference between the bottom layer and an arbitrary layer at height Z is equal to Z. Now here we have just used this linear gradient and just multiplied this with Z. That's why that is the reason why I insisted on just adding this thing, that they are very small values. Okay. All these things are actually mathematically not rigorous, but they are done very frequently to get the analysis done first of all in a simplistic manner, and then we do add gradually the sophistications. Okay, so finally rho 0 at a height Z, this is the initial density at a height Z, is equal to rho bottom times 1 plus alpha beta Z. Okay. Now remember that besides the energy equation, the momentum evolution equation should also satisfy the steady state condition with V is equal to 0. And then, like any other hydrostatic system under hydrostatic equilibrium in gravity, we can simply say dp0 dz is equal to minus rho 0 z g. Because if you remember the total setup, okay, the setup is actually vertically standing, let's say on Earth, on some places on Earth, or in a system where the gravity is actually acting vertically. So that I can draw over here. The gravity is actually vertically acting downward. Okay, so that is the direction of the gravity. Okay, so G is nothing but is equal to G times minus Ez cap. Okay, and if that is true, then you can simply write dp0 dz is equal to minus rho 0 z g. Okay, because G doesn't have any other component in x and y, along x and y, so dp0 dx is equal to 0 and dp0 dy is also equal to 0. Okay, so in the x and y directions, p0 is a constant throughout. Okay, now this is all about the initial configuration, which is a steady flow with a steady heating. Okay, and moreover, we are talking about not a flow but a steady state condition at rest. So this is a steady state hydrostatic condition. Okay. Now we want to perturb the whole system. We want to perturb it very weakly with respect to the initial steady state. The question is how to do that. Okay, can we do that? One very common process is to alter the rate of the steady heating. So you now play with the regulator of the burner. Okay, and let's say I am just increasing the regulator of the burner so that the heating rate is increased. Then T0 Z will now be coming some Tz. So T0Z was the temperature at T is equal to 0, I mean time is equal to 0, and now at any arbitrary time, the temperature at a layer, at a distance, at a height Z from the bottom is given by simply T, capital T, as a function of Z. Okay, and this Tz can be written as T0 plus T1. So this T1 is nothing but the first order or weak perturbation over T0. And what about rho z? Rho z is nothing but rho b 1 plus alpha beta z. That was the, already the initial value minus alpha times T1 because of this perturbed temperature. And finally, you can write rho z is nothing but equal to rho 0 z minus rho b alpha T1. Okay. And finally, for the perturbed pressure, Pz is equal to P0Z plus P1Z. Again, this is very weak. This is weak, we can easily understand because T1 itself is weak. Okay, so this is also weak with respect to P0. Now our system is perturbed. So it is assumed that the system is no longer in static equilibrium. So if the velocity is now perturbed from 0 to some v1, that v1 should not be equal to 0. v1 should be, and actually must be, non-zero. Then with, incorporating all these quantities, okay, in terms of its initial value plus its perturbed value, finally the momentum evolution equation can be written as rho 0 minus rho b alpha t1 times del t plus v1 dot nabla times v1. Okay, so this is the new total density for, at a place which is at a, height z from the bottom. V1 is the velocity of the fluid at that point, is equal to minus nabla, the total pressure P0 plus P1, plus rho 0 minus rho b alpha T1, that is the total density as well, times G plus mu nabla square V1. Okay, here somehow we have taken into account the viscous effect. Okay, and because most of the cases for the liquids the viscous effect is not negligible. Okay, and G, we just say that we are in such a system that G does not change much, and so there we neglect the perturbation in the G field. Okay, now we neglect, in this equation we neglect routine, this is a routine process, the second order contribution V1 dot nabla V1, and we also say that for the zeroth order contribution rho 0 G is equal to minus gradient of P0. So that is the initial condition. Okay. Plus there is another thing which is super important here. This is called the Boussinesq approximation, and this is the approximation with which this analysis becomes much more simpler. Otherwise it would have been much more lengthier and complex. What is that Boussinesq approximation? This simply says that since we are in nearly incompressible domain, the density variation only considered for the buoyancy term, because if the buoyancy term is, if we do not consider the density variation, this one, and we just say that this total term is almost equal to rho 0, then this rho 0 G will exactly be nullifying minus gradient of P0, and so there will be no buoyancy force. Okay, and actually the convection cannot be explained then, as you can easily understand. Okay, because as I said, the convection is nothing but the interplay of a vertical displacement, okay, of different type of fluids. So one is heated and gets lighter but still in the lower level, and one is colder, less heated, heavier, and still in the upper level. So this type of convective instability is there. So the lighter fluid moves up only because of buoyancy, right? And if the buoyancy force is absent, then the whole story is destroyed. Okay, if the buoyancy force is absent, then we cannot do anything to explain the convective motion. That's why we cannot neglect the density variation here. On the other hand, the density variation here does not play a much important role, because even with this one, okay, even with this one, the total thing, okay, because the total thing is almost equal to rho 0. So in this part we just neglect this increment. So the thing is very simple. Here the zeroth order term and the first order term both are intact. That's why I can neglect the first order contribution in front of the zeroth order contribution. Here the first order contribution, the zeroth order contribution is nullified by the zeroth order contribution over here. That's why I have to let the first order contribution survive. Simply this. Okay, and this rho basically then can be written as rho b plus, so this is, I mean, sometimes you can actually say rho 0, and rho 0 is also reasonably very near to rho b. Okay, and what is the, I mean, advantage of using rho b? Because rho b is a constant. Okay, rho b is the burner temperature in the initial state. Okay, as a result, the momentum equation becomes finally, so here you can see that rho, I mean, when I say about the perturbation of something like this, I said that the burner is, now that I have increased the regulator of the burner, this type of thing. That means also I can actually change this rho b, but where I am talking about this rho b, this means the rho b in the initial state. Okay, of course, even without touching the burner, we can actually make other heating source or other some source of energy which can heat up the system as well. Okay, now as a result, finally the momentum evolution equation becomes rho b del v del t is equal to minus gradient of p1 minus rho b alpha t1 g plus mu times nabla square v1. Okay, so finally we only have this term which is in the first order, this term the first order pressure gradient, the first order body force term which is nothing but the buoyancy term, and the viscous term which is also of the first order. Now let us linearize in the same way the energy equation. Okay, and if you do that properly, you will see del del t, t0 plus t1 plus. So the variation is only considered in the direction of z. So we can just simply write v dot nabla as v1z dz, and here within the bracket you have t0 plus t1, okay, is equal to kappa nabla square, then the total temperature is again t0 plus t1. Now we neglect v1z dt1 dz because of the second order problem. Okay, and dt0 del t0 del t is equal to 0 due to the initial steady state condition. Okay, also remember, due to, I mean, for this reason in the steady state we also had nabla square t0 is equal to 0. I mean, so you can simply say also that this del t0 okay, so I mean, so these three things, so this is neglected due to being second order term. That means this one, the second one, this one is 0, and this one here is 0 as well from the initial conditions. So finally the linearized equations, energy equation becomes del t1 del t is equal to v1zb beta plus kappa times nabla square t1. Okay, so finally we can see that we have this equation 1 and 2. So we have v1, we have t1, and actually we have p1 as well. Okay, and here we also have v1z. So we have actually roughly 3 unknowns, v1, p1 and t1. One simple trick can simplify the life just by taking double curl of this equation 1, and if you take that and if you note that double curl of any vector is equal to gradient of divergence of that vector minus Laplacian of that vector, and here since the velocity vector is divergence-less, double curl of the velocity vector will simply be equal to minus of Laplacian of the velocity vector. And if you correctly follow that identity and do the algebra carefully, you will find this equation will be this one and this one they get combined to give del del t nabla square v1z is equal to alpha g times d2 t1 del x2, sorry, del 2 t1 del x2 plus del 2 t1 del y2 plus nu times nabla to the power 4 v1z. Okay, and for V1x and V1y, we simply have a diffusion equation without any impact of temperature. That you can also check. Okay. So from 2 and 3, finally, we can evidently see that T1 and V1z are the two independent variables of the problem. So finally, if you have 2 and 3, you can easily see that you have two equations and two unknowns. One is T1 and one is V1z. That's even more interesting, okay? And handleable, okay? Manageable, okay? So considering the nature of the problem, so one can actually blindly propose for various type of solutions. Okay, we will here try to do some trial type of solutions of several types. So for this part of the discussion, we have finally see that the total Rayleigh-Bennett convection problem now gets reduced to two equations with two unknown variables. Okay, the more detailed discussion about the solution of the system will come in the next discussion. Okay, thank you.